In this video, I'm going to examine bivector geometry with a specific aim of looking at how to factor a two-blade, a bivector that is the product of two orthogonal factors, into its components. And that can be done a number of different ways, and we'll look at some of those ways and examine bivector products with vectors, factorization of a vector with respect to a bivector, and factorization of a bivector with respect to a vector. So we're specifically looking at two blades that have the form U wedge V. And if U and V are perpendicular, then that equals UV. So if we're given a bivector, for example, if let's say we have an arbitrary bivector in R3, so let's say we have A1, E2, 3 plus A2, E3, 1 plus A3, E1, 2. These are, if you notice, I've just taken the all the permutations, even permutations of 1, 2, 3 here as the components. There's a specific reason that I've done that. You'll see that when we look at how to express a bivector in terms of its normal, which you can do in R3. Anyways, if we have a bivector that's arbitrary like this, how do we find orthogonal factors for that bivector? So that's the motivating question that led to this video. But first we need to step backwards a little bit and look at the question of what happens when you multiply a vector times a bivector. So we'll start with the simplest case. Let's say we have R2 and some vector x equals A E1 plus B E2. Geometrically, that might be something like this: A B A E1 plus B E2. And I'm not going to bother drawing arrows over everything just because it's time consuming and messy. But if we have such a bivector and we multiply it by a unit bivector, let's call that I. So I'm going to write I equals E1, E2. And I'm calling this I because it has the behaviors of a complex imaginary. Specifically, if we have I squared, it's E1 times E2 times E1 times E2. I'm free to group these any way I want, and I can write that as E1 times minus E1 E2 times E2, which I can write as minus E1 squared, E2 squared. E1 squared is 1, E2 squared is 1, so this equals minus 1. Sure enough, I squared equals minus 1. Now, we're going to apply that unit imaginary, which is a bivector, to x, multiplying on the right, multiplying on the left, and see what happens. So if we take xi, what is that? E1, AE1 plus B E2 times E1 times E2, and I will sometimes write I equals E1, 2, which is what I did in the R3 case. That is just going to be short form for E1, E2. I didn't mention that earlier. So so we have E1 times E1, which is 1, times E2. So this first factor is just AE2. Now you have E2 times E1 times E2, which is the same as minus E1 times E2 times E2. So minus E1 times E2 squared, but E2 squared is minus 1. So that is minus E2. Now let's plot that, or graph that. I'll redraw. So if we have AE1, BE2, and we want AE2. So AE2 minus B, oops, that is B1. So minus BE1, and what do you know? You have a 90-degree rotation in the direction of E1 towards E2. That's what happens when we multiply on the right by E1, E2. So what happens if we multiply on the left? So IX in this case, E1, E2, E1, not A1, E1, plus B, E2. Now we have E1 times E2 times E1, which is minus E2, and we have E1 times E2 squared, which is E1, plus BE1. So minus E2A plus BE1 and now we have a rotation in the direction of E2 towards E1. So it rotated in a negative sense. So we see in R2 that bivector multiplication rotates by 90 degrees in one or the other direction, depending on the sense of the bivector. So if we had picked B equals 3 E1 E2, it would be rotate and scale. So rotate, scale. So in general, bivector multiplication is a rotate and scale operation. If we multiply a vector by a bivector that represents a vector that is in the plane of the bivector. So the next question is, what happens if we multiply a general vector by a bivector when that vector doesn't necessarily lie in the plane that bivector represents? So let's do that. So let's take R3 this time, and you could do an arbitrary Rn generalization of this question as well. It's going to give the same kind of answer. You'll see that by looking at the R3 case. So let's take A E1 plus B E2 plus C E3. And now let's multiply. I won't bother with left and right multiplication. I'll just do right multiplication in this case. Let's multiply by the pseudoscalar for the xy plane, which is E1, 2, or E1 times E2. So xi in this case is AE1 plus BE2 times E1, E2 plus C, E3, E1, E2. We've already done this part. We can do it again just as quickly. E1 squared is 1, so this is AE2 minus B E1 plus C E1, E2, E3. This is a unit pseudoscalar for R3. We usually call that one I, but and this is a vector that lies in the plane. It is a 1 vector. This is a 3 vector, or grade 3. So grade 1 and grade 3. So we see that if we take a vector, and you can generalize this to Rn, if we take any vector x times b, we end up with a vector plus a 3 vector. And that is the sloppiest vector. So we get a 1 vector plus a 3 vector. And we write that as x dot b plus x wedge b. So x dot b means the 1 vector component of xb, and x wedge b means the 3 vector component of xb, if it exists. This will be 0. This 3 vector term will be 0 if there is if x lies entirely in the plane of b. So suppose we want to examine what this means geometrically. And we'll get to that. But let's start with looking at taking a bivector with respect to a vector. So if we have, suppose that we have x lying in the, I'll use notation a bit, and say the span of B. Really we mean the span of orthogonal factors of B, but if we have such a vector, then B wedge x, or x wedge B, is going to be 0. So what happens now, we can decompose B into a factor that includes x and a factor that does not include x. And all we have to do is write B times 1, and we write 1 in a very special way as x divided by x. So there's a whole pile of mathematics where it's really useful to multiply by 1 in very special ways. You'll see it in quantum mechanics, where you write 1 as all of the kets. K, here, this is the same idea, where we take 1 as something times its inverse. We're going to do that twice in this video, once with vectors and once with bivectors, and take advantage of the fact that we can regroup. We can write this as bx times 1 over x, which is b dotted with x plus b wedged with x times 1 over x. But we've declared that b wedge x is 0, so we have now found a vector b dot x times another vector 1 over x as factors of the bivector b, provided b wedge x. So provided b wedge x is 0, we've now figured out a way to factor this. Factor a bivector into mutually orthogonal factors. We'd have to show specifically that these are orthogonal algebraically. We'll also see that geometrically in a little bit. We can write this out in different ways. We can say that this is b dot x times x over x squared. So now it's more clear. This is x inverse, but this is one vector factor of b, and this is another vector factor of b. And the reason that these are orthogonal is that, and we'll see this in a little bit, is that if we take, well, actually, we've already shown it. So if we have a plane, and I have some vector in the plane, if this is x, then xb is going to be, b dot x is going to be in one of these directions. This would be plus or minus b dot x, and this might be minus or plus b dot x. It would be orthogonal to x, So these are two orthogonal factors. So we've seen that b dot x is, if we dot that with x, it should be 0. And we can show that algebraically. Maybe we'll do that. Yeah, let's do that. So if we have, let's show, this is a problem, b dot x equals 0. So this is a vector, and this is a vector. We can just write that as the scalar selection of b dot x times x. And we've also seen that bx is b dot x plus b wedge x. So we can say that b dot x equals bx minus b wedge x. Plug that in. Bx minus b wedge x times x. Select the grade 0 component of that. So we have here b times x squared. X squared is a scalar, so we can pull that out. So we have here x squared times the grade 0 term of a bivector, which is 0, minus b wedge x times x, and this is grade 3, and this is grade 1. So we take a grade 3 multivector times a grade 1 multivector, we can get grades 2 and 4 from such a product. So that has no scalar term. So this is 0 and this is 0. So we've shown that b dot x, shown algebraically in general for any b and any x, that b dot x is 0. So that, if we were to plot this or graph that, what we're saying is that we have b and some vector x. We've seen that b dot x lies in the plane, and I'm going to cheat here a little bit. We haven't shown this. So there's the component here. Let's call this x parallel to the plane, and we'll call this part x perpendicular to the plane. What we saw in the R3 product is that b dot x, we really have to so we have our b dot x's are they lie in the plane. They happen to be perpendicular to x, and so b dot x is the portion of, essentially it's a portion to take the projection of x onto b and then rotate that 90 degrees in one of two directions. And we end up with a new vector perpendicular to x that lies in the plane. So that's geometrically what we're talking about when we say that b dot x with respect to the components of x that project or reject from the plane. Let's explore that a little bit more. And now what we're going to do is we're going to show compute or find, let's say, what our x parallel and x perpendicular with respect to b. And so now we do the trick of multiplying by 1. So x equals x times 1, and we're going to write that as x times b inverse. Now, we've assumed here that b has an inverse. So if b equals u wedge v, then both of u and v have to be non-null. So we can't have let's say we have if we had a relativistic space like the Dirac basis. So we couldn't have so gamma 1 plus gamma 0, if we square that, we get 0. So we're assuming that our factors of b are both orthogonal and non-null, which isn't really an issue if we're in R3 or some other, or in Rn. But so if we assume that b has an inverse, then we can write x as x times b inverse. And now we can write this as x dot b plus x wedge b inverse. Now, at this step that I skipped here is that I'm going to give ourselves a flexibility of grouping. So so we started with x times 1. Now we're going to regroup as x times b inverse. And we're going to span that. And so what we're left with is x dot b inverse plus x wedge b inverse. Now, b inverse is just b over b squared. So b squared is a scalar, b is a bivector. So this is a bivector that's proportional to b. So b inverse is proportional to b. And that means that if we have x dot b, which lies in the plane of b, and we multiply it by b inverse, which is proportional to b, then it rotates x dot b. So this component here still lies within the plane of b. And whereas this component necessarily must lie outside of the plane of b. And we can show that algebraically by computing the inner product of the two. So let's say show, and I'm going to identify this as x parallel and this as x perpendicular. We've seen that this is parallel. What we wanted to show that this is the perpendicular component, we want to show that the dot product of the two is 0. So that would justify that labeling. So I'm going to show that x parallel dotted with x perpendicular equals 0. And let's do that. So x parallel dotted with x perpendicular is, we write the dot product. So we write a dot b again as the scalar part of ab. And here we have x dot b inverse times x wedge b inverse. And take the scalar part of this entire messy expression. Now we will utilize our flexibility. So this is a vector. And if we apply the reversion operation to all terms of this multivector expression, then we end up with still having a vector. So we can write this as x dot b times b inverse. That part is unchanged. Now if we reverse this, we get b inverse reverse, and the reverse is going to flip the sign. So we reverse that, and then we reverse b wedged with x. So each of these reversions just flips the sign, so we're left with b inverse b wedged x. And another way of seeing that is if we take x is going to be b inverse bx, so that's just b inverse b dot x plus b wedge x, so it's b inverse b dot x plus b inverse b wedge x. So this is a different way of writing x parallel, and this is a different way of writing x perpendicular. So we're free to now say b inverse times b inverse b wedge x, all scalar. That was a kind of roundabout expansion, but the key here is that b inverse times b is a scalar. So now we're left, and so we can pull that out. Let's do that. So let's say, and then we're left with x dot b times b wedge x. We want the grade 0 term of this multivector product. This is a vector, this is a trivector, and means that the product has grades 2 and 4. That's grades 3 minus 1 and grades 3 plus 1, and means that there is no grade 0 term. So that multivector, x dot b times b wedge x, has only grades 2 and 4 components, no grade 0 component. So if we select only grade 0 component, which is what we're doing, we have 0. So that says that we have identified x parallel. We identified x parallel geometrically as x dot b times b inverse, or b inverse b dot x, and we identify x perpendicular as x wedge b inverse, or as b inverse b wedge x. So we have two different ways of writing this thing. So if this is b and that is x, so we have here two components. This first one is x wedge b inverse, and this one is x dot b inverse. And in particular, let's also say if we have b squared is minus 1, so b is a unit bivector, then we have the nice case of x parallel is x dot b, and x perpendicular is x wedge b. So if that was the case, then you see that this illustrates why x dot b is this component here, or this component here. This is x dot b. Plus or minus x dot b, minus plus x dot b, where the actual direction of this vector depends on the orientation of b and x with respect to the plane. Anyways, so this is the geometry of decomposition of a vector x into the projection with respect to b, and the rejection. So we could say a little bit more formally that the projection of x onto b equals x dot b, the inverse, and the rejection of x onto b, or rejection of b from x is x wedge b, the inverse. And in a particular case where b is a unit bivector, then we can get rid of the inversions and just say this is x dot b times b and x wedge b times b. So that is the geometry. We've shown that x is perpendicular to x dot b, and we've shown that x dot b is perpendicular to the projection of x onto b, and we have found we've found algebraic expressions for the projection and the rejection. That is most of what we're interested in algebraically that relates bivectors and vectors. So now we want to move on to factors. So how do we find b equals uv given any b? And let's consider the R3 case. So if we have, let's say, b equals e12 plus e23 plus e31. So some combination of all of the unit, so as an example. So we've seen that if we take a vector in the plane, so let's take one of uv. So if b wedge u is 0, b wedge v is 0, then b dot u lies in the plane, and b dot v lies in the plane. So our plane is actually spanned by those two vectors. But how would we find a vector that lies in the plane if all we have is a bivector? The answer to that is that so in an expression like this, where E1, some vector that contains E1 or E2 or E3 has to lie in the plane that to B represents. So we could really just arbitrarily pick one and find that projection onto the plane by taking the dot product. So let's say b dot E1. So that will be E12 plus E23 plus E31 dotted with E1, and E12 dotted with E1 is minus E2, E23 dotted with E1 is 0, and E31 dotted with E1 is E3. So we're left with E minus E2 plus E3. So there's a vector in the plane represented by B. So we can compute an arbitrary dot product, find its projection. So if we had this plane and suppose that was E1, then we just found this vector b dot E1. That lies in the plane. If we rotate again, by multiplying it by b, we find another vector that lies in the plane. So all we have to do now is we have to take b dot e1 and multiply again by b. Let's put it on this side. And if we do that, and we don't have to take a dot product this time because b dot e1 lies in the plane, so it will have no trivector component if we multiply b dot e1 times b. So that's e1 2 plus e2 3 plus e3 1 times minus e2 plus e3. And so this gets a little bit messier and longer. So e2 times e2 squared is, so we have minus e1. Yeah. Minus e3, that's e2 3 times minus e2. Oh, no, that is plus e3. So e2, e3, e2 is plus e2 squared e3. So that's e3. And e3 1 times e2 will have no vector component, so we could skip that. But and now e3 times e1 2 also has no vector component. The two of those should be matched. So if we have e3 1 times minus e2, that is going to be minus e1 2 3. And over here we have e1 2 times e3, which is just plus e1 2 3. So those, we see those components cancel out, and we are left with e2 3 times, oh, we did that one. So e2 3 times e3, which is e2, so 2, and e3 1 times e3, which is minus e1. So we're left with minus 2e1 plus e2 plus e3. So we see that the plane that's represented by b is the span of minus e2 plus e3 minus 2e1 plus e2 plus e3. And you might think that we just got lucky by picking one vector. We could do the same kind of thing for picking e2 or e3 as the vector and dotting that. So if we took b dot e2, b dot e3, e1 2 plus e2 3 plus e3 1 dotted with e2 dotted with e3. Here we get e1 minus e3, and here we get e2 minus e1. So we have e1 minus e3, e2 minus e1, e3 minus e2, and minus 2 e1 plus e2 plus e3. These are all vectors that are, let's write that, these are all within B. There's quite a wide variability here in terms of the vectors that we found. We can make a little bit more sense of that if we look at the B in terms of its normal. So if we write B equals in for some n normal to B, so here there's going to be some n that in R3. So in R3, we can write b in terms of its normal, and this is why we have the cross product giving the normal to the plane. We do the same thing for bivectors, and if we do that, let's say that b equals a1, e2, 3 plus a2, e3, 1 plus a3, e1, 2. So we can compute and so the net n equals minus ib or minus bi. The pseudoscalar I, it commutes with all grades in R3, so it's convenient that we can move it around if we desire. And what do we have? We have minus a1, e2, 3, 1, 2, 3, plus a2, e3, 1, 1, 2, 3, plus a3, e1, 2, 1, 2, 3. And so e2 times e3 times e1 times e2 times e3. We can permute this so that it's e2, 3 squared times e1, which is minus 1 times e1, which, so minus 1, and we're left with plus 1. So that is plus a1, e1. Now if we look at our next term, we have e3, e1, e1, e2, e3. e1 squared is 1, so we're left with e3 times e2 times e3, which is minus e2, e3 squared, which is minus e2, so it's minus again. And we're left with plus a2, e2, and you see the pattern here. So e1, 2, 1, 2 is e1, 2 squared, which is minus 1 times e3, which is minus e3, but minus e3 is plus e3, so we're left with a3, e3. So when we pick this way of writing our bivector, it happens to be all the permutations written out in this way nicely. It is another way of saying it's like the normal form of the bivector, because it's dual to this normal that has a1, e1 plus a2, e2 plus a3, e3 components. So if we were to look at, so we had b equals e1, 2 plus e2, 3 plus e3, 1. What is the normal to that? So that is minus e1, 2 plus e2, 3 plus e3, 1 times e1 times e2 times e3. So e1, 2 squared is minus 1 times e3. So we have e3 and e2, 3 times e1, e2, e3 is minus e1. So minus 1 c1 is e1, and e1 times e1 is 1. So we're left with e3 times e2 times e3. e3 times e2 times e3, which is minus e2. Minus e2 is e2. And so that, we go back and look at, here's the vectors that we were finding that were in the plane. So E1 times E3, E2, or E1 minus E3, E2 minus E1, E3 minus E2, minus 2E1 plus E2 plus E3. All of these are, if you dot them with E1 plus E2 plus E3, that's going to give you 0, 0, 0, minus 2 plus 2, which is 0. So that kind of shows that we just found, for this particular bivector, we were able to split it into various components. So one of those was minus 2E1 plus E2 plus E3. And if we looked at the, let's say we have the unit bivector, so 1 over root 6 will be one factor, and the other was E3 minus E2. So that's one way of factoring our bivector into two different components, each mutually perpendicular, and in this case, mutually orthogonal. All we have to do is, so this one was b hat dot E1, and this one is b hat dot E1. Now we can do the same thing for if we project E2 or E3 onto B. The only place we really need to be careful is if we want to pick, let's say we had B equals 10 to the minus 7, E12 plus 10 to the minus 9, E23 plus 10 to the 8, E 1, 2, 2, 3, 3, 1. So something like this, you wouldn't want to be arbitrary and pick. We especially wouldn't want to pick E2. So here, don't pick E2 as to project. So if you're computing, pick some vector and take b dot that vector. So we don't want to pick E2 because all of the contributions of E2 here are going to be extremely small, and you'll end up with something numerically ill-conditioned. So what you want to do is pick E3, E equals E3 or E1 as factors, and compute the projection of that. So if you did that, really you want to pick, so if you have a bivector like this, pick the one that has the largest absolute magnitude component or coordinate. And so picking E3 or E1, the factors of the unit bivector for that component, pick those and then project that. So if you do that, you'll get, let's say, if we picked E3, so b dot E3 is going to be 10 to the minus 9, E2 minus 10 to the 8, E1. So this way you don't pick, you've got something here where you pick the primary contribution, and now if you're going to go and then take b dot E3, you'll get something well formed for the second factor, and you'll it won't be screwed up by the fact that had you picked E2, you would, yeah, anyways, you could get into trouble. So those, most of the things I was going to discuss. There's one more thing to discuss, and we've already looked at some of that. So again, in R3, where we can say that B equals I n, let's look at what is B dot x in terms of B. In terms of n. So let's compute that. So B dot x is a vector. So we can take the grade 1 selection of bx, which is inx, and we group as nx 1. So this is I n dot x plus n wedge x. And this is where it becomes unfortunate that I picked x as my variable. So let us just say, let x equals a. N dot a plus n wedge a. This is just because. So n dot a is a scalar. And there we have a trivector. So this product, this multivector product is a trivector, so it has no grade 1 term, so that is 0. We're left with n wedge a 1, and n wedge a we can write as cross product as I n cross a. And now we have I squared, which is minus 1, times n cross a, which is a vector, so we select the vector, which is just plus a cross n. So we have b dot a equals a cross n. There is the dual form of this bivector product. So if we looked at that geometrically, that is n, and this is a, then projecting onto the plane, we have here right-hand rule. This one here is a cross n equals b dot a. So we can, the duality relationship of b equals in allows us to reinterpret this dot product as just a cross product. And in particular, if this was a unit normal n, then if we rotate, we would multiply by n again. So we would find that b dot a is going to be, that will be b dot a cross n, which is a cross n cross n. So we have two equivalent ways of writing the product, the factors. So we can say that if we had a unit bivector b hat, it will be equal to b dot a, where if And let's suppose that E dot A well, it's going to be proportional to, don't worry about signs, B dot A. So that's one way of factoring it. Or we can say that two factors are going to be A cross N, and A cross N. So there's two other factors. So we can write the factors in terms of bivector dot products, or we can write the factors in terms of vector cross products, whatever is most convenient. With the caveat being that we can only use this form of factorization in R3. So this is for R3, and this is for Rn. So two different ways of factorizing. We can make use of the normal to the plane if it's convenient. We can use a bivector dot products or cross products, whatever is most suited. And we've also looked at projection and rejection, components of a vector with respect to a blade, components of a blade with respect to a vector. And that is pretty much it for the basic geometry of bivectors and vector relationships in geometric algebra in Rn and R3, with a little hint of how you would approach this in non-Euclidean spaces, like relativistic spaces.